Now I will go to the some more advanced topic. Let's understand the measurement and the matrix. So there's a Copenhagen interpretation. We call it Bond's rule or Bond's rule, right? It says if an observable corresponding to a self-adjoint Hermitian operator A with discrete spectrum is measured in a system with normalized wave function, then the result will be one of the eigenvalues number I of A. You don't know what I'm talking about. What is observable? Observable is talking about something we can measure. Quantum mechanics has many things that we cannot measure, but there's something we can measure. For example, the spin, the energy, the position, the momentum. They are called the observable. And each observable is correspond to an operator, like a matrix, what we said before. For example, the spin up and down, right? That spin is correspond to the sigma z, right? That operator, right? So, for example, spin, the observable can be spin, and the operator can be sigma z. And that operator needs to be Hermitian and self-adjoint. What is this? I'm going to teach you later. You don't know, right? It has a discrete spectrum. It means it's not continuous. For example, the spin is either up and down. Okay? So when you do the measurement of the observable that is corresponding to the self-adjoint matrix A, you will get one of the eigenvalue, and that is why eigenvalue is so important. For example, here, if A is sigma z, then the eigenvalue lambda I will be plus minus 1. Yeah, either spin up or spin down. Okay? The probability of getting it is equal to this. Wow, this is very difficult. It is the projection operator. We won't talk about this yet. It's going to spend more time for us to talk about this. But after this slide, we're going to explain everything so you can understand what it actually is doing. Okay? So let's start with the most basic thing, the adjoint of a matrix and the so-called Hermitian matrix. What is the adjoint of a matrix? For example, if I have matrix A, okay, is adjoint a name, right? Is A dagger. Okay, we label the adjoint of a matrix as A dagger. How do you get it? By transpose and compress conjugate. Okay, by transpose and compress conjugate, which means A dagger must be A transpose and then compress conjugate. Okay, you are very familiar with this. Oh, you ring the bell, right? Isn't that is like what we're doing for the bra cat? We start with cat and then we get bra. We will do transpose and compress conjugate. That is for the vector. And now this is for the matrix, right? They have some relationship. But now just learn the definition of adjoint, which is A dagger. Okay? Now, if for a matrix, if A equals to A dagger, right? I do the transpose and compress conjugate, and they are the same. It's just like I look into the mirror, I get exactly the same thing as me. Then A is the Hermitian matrix. Please memorize this definition. Hermitian, okay? A very important property you will see later. All the observable matrix needs to be Hermitian because they have real eigenvalue. Okay? But now just learn the definition. Let's take an example. For example, if A equals to I, 0, 1, right? This is a two-dimensional matrix, 2 by 2. What is A dagger? Well, as I said, it is A transpose star, right? So it is going to be I, 0, 1 transpose stars. When I do the transpose, it is I, 0, 1. Transpose means you make the column to row, the row to column, right? So this column becomes row, so it's I. This column 0, 1 becomes another row, so it is 0, 1. And then the whole thing, you take the complex conjugate. So what is this? Complex conjugates, again, you only negate the imaginary part. So yeah, it becomes negative I, 0, 1. And definitely A is not equal to A dagger. So it is not Hermitian. Not Hermitian, okay? It's not Hermitian, not very interesting. And we know that this matrix cannot be an observable. Cannot be an observable. Okay, how about this one? You know what is sigma y, right? We just learned it. What is sigma y? Sigma y is the matrix corresponding to the magnetic field in the y direction that we use to measure the spin. And this is 0, negative I, 0. Okay? Let's try to see what is sigma y dagger. What is that? First, I will do the transpose. So the row, first row becomes the first column. Second row becomes the second column. And then I need to take the transpose. I mean the complex conjugate. Then I get negative I, 0. Oh, what is this? Sigma y. The transpose equal the adjoint of itself equals to itself. So it is a Hermitian. Okay, so this is an example. Hermitian matrix. Okay, so here we introduce the so-called Hermitian matrix. Okay. Now we have learned Hermitian matrix, then we have a chance to learn the bracket operation again. Because now we don't just have the the vector and scalar. Now we have the matrix. Okay, so how it works? So we remember that if I have cat, I have a dual correspondence with the bra. Okay, for example, cat alpha correspond to bra alpha. Okay, now what if I have a matrix X applied to alpha? Remember, this is a matrix applied to a vector. What do you get? A vector. So a vector still have a dual correspondence, and this is what we have. Just memorize it. It's very similar to the complex coefficient, right? But you need to put the matrix to the right of the bra, and you use the Hermitian of X to do the operation. Okay? And now we also have this. If I have two matrices, X applied to X to alpha equals to Y applied to alpha for all alpha. So for any vector, you have two matrices, which is two operations. You apply to this any alpha, and they are still the same. Then it means that the matrix are the same. Okay, this is a way to prove. The third one is that we have something called null operator. It is just like the zero. It applies to any vector, it gives you the zero vector. But remember, this is not zero. This is still a vector. You get this. If you put it into the column form, you get this. Everything is zero. It's just saying that I have zero components of the first basis, zero component of the second basis, etc. But this is not a number, it is still a vector. Okay? Now, very similarly, if I have a vector, I have a matrix applied to a linear combination of two vectors, like C alpha, C beta, C alpha times alpha, C beta times beta. Of course, I still get a vector, right? You apply a matrix to a vector. A matrix is just do an operation on the vector. And as we say, particularly in quantum computing, it does nothing but just doing the rotation, right? You still have the vector, but then you get the, so you have a bra version. And how do you find the bra version? It's just like what we did earlier. You get the complex conjugate of all the coefficients and then multiply to the bra version of alpha, complex coefficient, multiply to the bra version of beta, but then on the right, you multiply the adjoint matrix of X. Okay? So these are just the rule, but you need to be familiar with them, right? You can have a cheat sheet, you can Google, go to Wikipedia, but the more is that you need to understand which one is scalar and which one is vector. Okay, that need to be very careful. Now, the last rule I want to tell you is the so-called association property. This is very important. Okay, associate property is very useful. That is what confused you just now when I talk about the projection. What does it mean? It basically saying I have a bra version of beta, multiply to the matrix, and then multiply to the ket. Okay? So the association property say that to find this one, I can first just apply the matrix to the bra to get a bra version of the vector and then multiply it to the ket. So this is still a bra, right? Or I can also first multiply the matrix to the ket to get the ket and then apply it to the bra. That is the meaning of this associative property. So we can group them as you wish. Okay? Now, do you remember that since A inner product with B equal to B inner product with A star? Okay? Do you remember this? Then beta X. Again, what is this? This is a bra. It's just like A. Inner product with alpha. Isn't that it's just like putting alpha as the bra and then find the ket version of the beta times X, right? Which is X dagger beta, right? This is a little bit confusing. Let me say again. This is A, right? And this is like A. Okay? And then this is B, which is the ket. So here I have the alpha, which is the ket. On the right hand side, it becomes the bra. So here it becomes the bra, right? So we say that A inner product with B equals to B inner product with A and compressed coefficient. This one is also a number because I apply the operator to beta. It becomes a bra times A equals to the A as a bra times the operator by the ket of this version. But we already said that what is the version? What is the ket representation of this one? It is just equal to ket, but then you need to do the adjoint matrix of X, right? So it means this one, of course, I need to also put this star. Okay, so because of this, you see that now I don't separate them, I just write them as the whole beta X alpha equals to alpha X dagger alpha, this is beta. Okay, so you see that if I swap everything, all I need to do is just to add compress conjugate to the real number, the whole thing, to the number, the whole thing is a scalar, right? Add compress conjugate to it. And add the adjoint to the matrix and change the bra to cat and cat to bra. The results are still the same. Okay? Find the eigenvalue. Why the adjoint matrix is so special, right? Why it is real. So this is the claim. If A equals to A dagger, it means it is Hermitian. Okay, that's the definition we said, right? Then its eigenvalues are real. Okay, if it is Hermitian, its eigenvalues are real. And that is what we are going to prove, okay? So I was going to let the eigenvalue be lambda I. Okay? And eigenvector be lambda I, but I put in the cat, now becomes a cat, right? Again, the cat is just a symbol. I can put anything, right? I put lambda I, it means it's the eigenvector correspond to the eigenvalue lambda I, which means A times lambda I, the vector, equals to lambda I, the eigenvalue, times lambda I, the vector. Is this okay?
Why is the eigenvalue and the eigenvector the same?
Why do you think this get it mixed? Lambda I in the cat. What is the meaning I write something inside the cat? It's just a vector. And I put lambda, I say this is the vector correspond to lambda I. Right? If I put A, you lose the information. I know it's confusing, but this is exactly what it means. This is the vector, the eigenvector correspond to the lambda, the eigenvalue lambda I. Or how will you write it to be better? Should I write in English? The vector correspond to lambda value, eigenvalue lambda I. That would be very clear, right? A times the vector with the eigenvalue lambda I equals to lambda I times the vector with the eigenvalue lambda I. Do you remember at the beginning of the class, I say the polarization of the photon, right? Or something, I can say a really long sentence, and when there's no ambiguity, I can just put a simple. How about this? You think about that, what you can write to make this less confusing or better than this? With the C. You mean here with the C? Then how do I know C is for lambda I? I can be 0, 1, 2, 3, 4, 5. What will you write? CI. Then if you put CI, why don't I put lambda I? What's the difference between CI and lambda I?
Two different things, because one is a vector, the other one is an eigenvalue.
No, the vector is enclosed by this bracket. It's very clear this is scalar, this is vector.
That's true, but using the same name and confusion.
I do not have confusion because they do corresponding to each other. That is what I want to mention.
Okay, so
right?
So you can maybe emphasize that there's a relationship between the two.
There is a very clear relation. That's why I say this vector is equivalent to writing in English. Let me write this down, right? I think everyone needs to agree with me. Basically, what I write just now is A times the vector that gives, let me write it better, right? A times the vector, or even I should say, A times the eigenvector corresponding to eigenvalue lambda I equals to lambda I times the eigenvector corresponding to eigenvalue lambda I. Would this be clear?
Sure, it will be clear, but after eigenvector, I would have added lambda I.
No, if you get confused, we need to make this clear. What's wrong with this sentence? A matrix times the vector corresponding to eigenvalue lambda I equals to lambda I times an eigenvector corresponding to eigenvalue lambda I. That is the definition of lambda of eigenvalue and eigenvector, right?
Yeah, but lambda
No, lambda I is not eigenvector. Lambda I is eigenvalue. But I have a vector corresponding to eigenvalue lambda I. When you have this eigenvector, you get this eigenvalue.
okay, the reason I'm getting you put lambda I.
No, don't talk about this yet. I'm asking you, is this the most clearest notation about this relationship of eigenvector and eigenvalue?
Yes.
If we allow to be so, lengthy, right? Is it the clearest? Then, if we agree that I can just put lambda I because this is just a symbol, everything is just a eigenvector corresponding value lambda I. I put lambda I here. And then I know this is talking about the vector that corresponds to the eigenvalue lambda I. Right? I know that you say you want to put this to C1. Ci. But if this is clear, a vector corresponding to lambda I, you put Ci, then it's really confusing. Why you say it corresponds to lambda I, and then now the eigenvalue is Ci? Is Ci equal to lambda I? Yes. And then why don't you put lambda I? Okay, think about that. Anyway, yeah. No. This is matrix times the vector equals to the eigenvalue times the vector. What is the meaning of eigenvalue and matrix? A times a vector may be, let's use the normal form, V times V equals to, let's say, alpha times V. Then we say that alpha is the eigenvalue and V is the eigenvector. That's the definition of eigenvalue and eigenvector. Okay? Remember this? What is eigenvalue and if you forgot, trust me, you need to memorize it. You apply a matrix to a vector, it becomes that vector times a number. Then that is the eigenvector, and that number is the eigenvalue, and that is the definition. That's it. No more confusion. You need to agree that. That is a definition. What? A is what? Okay, everyone need to think very carefully. What is matrix? What is matter? What is number? But this is very important. No problem, right? We need to figure this out. Otherwise, you cannot move forward. A is a matrix. Like this. Just like this. 1, 0, 0, negative 1 times 1, 0 equals to 1 times 1, 0. This is A. This is V. This is alpha. A matrix times vector equal a number times the vector. So this is the eigenvector. This is the eigenvalue. Okay? Here is what it's saying. The matrix times the eigenvector equals to the eigenvalue times the eigenvector. Right? That's why I have this one. This is basically like A times lambda 0 equals to lambda 0 times lambda 0. Because this 1, 0 corresponds to lambda 0. Lambda 0 is 1 in this case. Yeah.
So is this notation?
Very common if you want to look at very complicated equation. Because by here, I know they is corresponding to this guy already, right? Why I want to write so long, why I want to become Ci, and then say, oh, Ci actually is lambda I. Same problem for me when I study it. So that's why I force you to trust me and immerse you. So I hope you be very familiar with this. I have the same problem, even worse than you guys. Okay, so you need to accept it to be very familiar with it, because once you have this later, the equation will be very easy for you. But if you still feel uncomfortable with this, then later you will get messed up very easily. Okay, very good question. So I spent a lot of space already. So let's prove it, right? So now I apply the lambda I bra. What is this? It's a vector number or what? Matrix? Vector, but what form? The bra, right? Apply the bra to this guy. Okay, we apply bra to this guy. Is this valid? Yes, because this is what? Vector? This is matrix. What is matrix times vector? Still vector in the cat space. Bra operates on it, becomes what? What is the bra on cat? Scalar. It's just an inner product, right? Do it step by step. Cat times matrix, still cat. I just rotate my vector. It's still a vector. Then I do an inner product with the bra. This is another vector, right? So apply this. Same thing I will apply to the right-hand side. Now, I know this is confusing, right? If you did not come to other classes, you come in this class the first time, you will just don't know what I'm talking about, right? But you are good enough. You should know that this must be a bra because it's between this one, right? You won't try to find out, you won't say, hey, this is the absolute value of lambda I, and then have something hanging over there, right? You need to take it, right? So this is the bra, this is the cat, and what is this then? What is that? A lumber, right? So basically you have a lumber here, right? So what can I do with the lumber? I can just take it out. Correct? Because if you don't not happy with this, just go back to the basic. A lumber times a vector, and then do the inner product with another guy. It's just the same as take the lumber out, do the inner product first. Okay? Yeah.
So I guess let's say I said, oh, there's a vector in the first one is a vector, middle one is a vector, and the third one is a vector. That will be incorrect.
Exactly.
You can't.
Well, you cannot have two vectors multiply together unless you have a new definition. But at least in this class, we don't have this, right? So you need to guess in that way, because in the future you read the paper, you need to be very clear to you. Okay? Good. What is lambda I? Inner product lambda I. Huh? Scalar, what is the value? It's a scalar, correct. I need to tell you that I assume all are normalized. Lambda I squared, correct. And then I assume it is normalized. What would that be, a lambda I squared? 1, yeah. Which is lambda I squared, you're correct, right? I assume it is normalized. I did not say that, but here I assume it is normalized because we're doing quantum computing, right? Okay, good. So this is equation 1, right? So now then I will do this. Because of this, then I'm going to apply the compress conjugate, okay? I just say apply star. Then what happened? On the left-hand side, I have lambda I, A, lambda I, star. Right-hand side is lambda I, star. Correct? Make sense? I just apply from both left and right are both numbers, right? Now this one, you need to memorize it. And I showed you last time. If I swap it, right? A, X, B, where X is the operator matrix, I become B, X. It is still the same if I apply the star on the outside and then put it as dagger. Right? So we did that last time. It is equal to lambda I, A dagger, lambda I, and then I put the star, so the star is gone. Particularly, I want you to know that I already done this to here, and this to here. Right? Just like the AB, swap that. And then here is actually I have 2 stars. Originally, I have a star. I add 1 more star, compress conjugate, and then compress conjugate, it means nothing. Right? That's what it is doing here. A becomes A, B becomes B, and I put compress the adjoint matrix, and I put the star, then they are the same. That's what I'm doing. Here become here, this one becomes this, and put compress conjugate. I mean, put the adjoint matrix, and then add 1 more compress conjugate, but these 2 cancel out, right? Question? So here is to the whole thing, because what is this whole thing? Is it a number, matrix? You can do all the multi-operation. It becomes what? This whole thing. Scalar becomes a number. So what it means is just apply the compress conjugate to a number. How exactly you can do it before you do multiplication? You actually apply to them individually. You can do that because that is how it operates, right? But you don't need to think about that now because I treat the whole thing as a number. Okay? So then what does it mean? Left equals to right. Right? So this one, or maybe I'm, okay. But since A is Hermitian, I'm a little bit too long today. A equals to A dagger. Then this one is also equal to lambda I, A lambda I. Right? I apply one more time. I just look at this one because A dagger equal to A because it's Hermitian. I can write this as A, right? Then it means this guy equal to this one, right? I call this equation 2. Then from 1 and 2, what do you get? 1 is on the left-hand side is this one. 2 at the left-hand side is this one. They are the same. Then it means what? Lambda I equals to lambda I star. Then what is the meaning? It's real. Because its compress conjugate equals to itself. Then lambda I must be real. Okay? I think I overrun, right? But it's a good discussion, actually, very important. Just hold on. Let me Yes, question? How come what? Say again? No, because star got cancelled. You start with one star, and then when I apply the equation, I need to add one more star. You see? Here is no star. When I do this swapping, I need to add one more star. Yeah. So that's why these two cancel. So that's why it's gone. Okay, good. Other questions?
Professor, you're gonna be